This presentation will cover Fabric Semantic Models as the foundation for good math with AI agents and agentic solutions. It's a recorded version of the presentation that I gave for SQL Saturday 2025 in Minnesota. The original version was given in September of 2025. So to quickly review what you can expect during this video, I'll cover why it's important to have good math within agents and agentic solutions. We all know that large language models and AI are fantastic with text, but what about when you need to run calculations on large volumes of data? And by calculations, I mean math. I'll quickly review how Fabric data agents fit into this equation, discuss how this relates to semantic models, which has been a longstanding capability within Fabric and Power BI, and then I'll get into some best practices for preventing hallucinations when you're building agentic solutions and making sure that you get good math on your data. Finally, I'll talk about how this is going to impact data professionals long-term. And the demo that I show within this video is available via GitHub, and anybody can download and use it. So I'll show you how to go ahead and get that, and you can install it into your own environment within Fabric. Some quick background information. I've been at Microsoft for over 9 years now. I work in the healthcare division. I like to joke that I've been working with Microsoft BI since the days of ProClarity and SQL Server 2005. And feel free to add me on LinkedIn. And I have a blog with all of my historical information, which you can follow for future content. So everywhere you look, every news story you read, widespread within the tech world, we're hearing that AI is transforming the world, but data is the fuel that powers AI. And when we're in a period of paradigm change, such as the one that we're in right now, it's very easy to focus on what's new and forget about what's needed from the old in order to make the new work to the best of its capabilities. There's an old saying in the data world of garbage in, garbage out, that if you put bad data into a solution, you're going to get bad results out of the solution. The same thing applies to AI. These large language models are fantastic. Agentic solutions have a tremendous amount of potential, but if there is not a solid foundation of well-architected, carefully thought out, modeled data underneath it, you will not get the best possible results out of your investment. By now, most of the people watching this video have probably heard of Microsoft Fabric, but effectively, if I were to summarize it in a quick elevator pitch, it's a software as a service portal that allows you to spin up different Azure resources by pushing a button in that portal, and everything deployed will be integrated, secured, handled by Microsoft on the back end, and it all rolls up to a single billing mechanism. Whether you're building solutions for AI, for data and analytics, for data science, there are tools within Fabric to enable you to get going on your project quickly and spend as little as time possible working on infrastructure, networking, setting up security, those sorts of things. Additionally, the Fabric platform allows you to connect to all of the data in your environment while also serving as a database when it's appropriate to put the data within Fabric. So why a presentation about semantic models and AI? How does this all come together? So if you've read up on AI and large language models, we all know they're prone to hallucinations. I put a link in my deck to the OpenAI paper about why large language models hallucinate. And what this basically comes down to is that large language models are fundamentally not designed to do mathematics. They're effectively an autocomplete mechanism, and mathematics follow a very different logical progression. There are newer large language models that can do math and work their way through some of these complex problems, but quite often those queries take a long time to run and they can use a lot of compute. Having access to a traditional structured database endpoint with the appropriate mechanisms to run good queries is one way to overcome this limitation of large language models. One of the topics that I think people everywhere who are using AI for solutions need to consider is that good math matters and bad math can have catastrophic consequences. I always like to go back to the Mars Climate Orbiter in 1999, which crashed on the surface of Mars because one team was using newtons per second for their calculations, where the other team was using pounds per second for their calculations. It sounds silly, but when we think of an AI application or an agentic solution which is using AI, and you might deploy it to a worldwide audience, when somebody talks about a measurement in Europe, it might be different than a measurement in the United States, and even from company to company, terms might mean different things. How is the AI agent supposed to know specifically how to interpret those terms? How do we make sure that when somebody gets a result from a question they ask an agent, or even if an agent is acting autonomously, that it doesn't act on bad numbers? Now, just for fun, I put this together with Microsoft 365 Copilot. When we're all in college, we learn that there's no such thing as a stupid question. As we get out in the real world, we learn that there's actually a lot of stupid questions and they're everywhere. And what worries me is that as we get into the era of AI, that people are going to enter these stupid questions into the chat bots, they're going to get stupid answers, and they're going to make stupid decisions. So how do we make sure that we don't metaphorically crash the Mars orbiter into the surface of the planet? Now, just to level set with some of the terminology that I'm using in this video, when we're talking about Copilot and Microsoft Fabric, there are several different products that are referred to as Copilot under the Fabric umbrella. What I'll be showing today is specific to Power BI Copilot and then also Fabric Data Agent, which is not on this slide. Power BI Copilot is a set of capabilities to use AI with analytic reports and tools designed to provide answers from your data. When I talk about Fabric Data Agents, they do have some overlap with Power BI Copilot from a Venn diagram perspective, but data agents are fundamentally a way to run structured queries over your data and provide an endpoint to external tools, such as Copilot Studio or Teams or AI Foundry. And within Fabric Data Agents, the context and configurations is what I consider to be the most important part of that tool and the most important consideration that you should work on when building out these types of solutions. I'll explain that a little bit more during this presentation. So I want to walk through a slide that I put together that reviews the different layers of an agentic solution and where the real value is going to lie at scale. So long term, after all the dust settles, how are you going to be able to differentiate your solutions from competitors? And also, where should you be putting your IP and your effort? So if we think about the data storage layer, which is where the relational data or even the unstructured data is getting stored, that layer has become a cheap commodity. All the different cloud providers offer it. The cost is, less than, pennies per gigabyte per month. And effectively, everybody out there has access to the same scalable, nearly limitless storage capabilities. The next layer up is where the queries actually get calculated from a relational database perspective, and also where AI is running large language models in order to interpret natural language and provide a response. Both of these are also quickly becoming commoditized, where there's multiple competitors on the market available in multiple clouds, and the compute costs with all the new models continue to trend downward. So it's getting less and less expensive to use these tools. Also, relational database query costs have come down. If you look at the cost to run extremely large queries 10 or 20 years ago versus today, it is something that is deflationary, not inflationary. Next in the layer is that semantic context and configuration. And this is the fundamental crux of the presentation, that the semantic layer may be the most important layer in your entire agentic solution. Effectively, if you are in the financial world and you have a unique way to value financial products, that logic is usually baked into this level. If you're in the healthcare world, this is where you are determining how to calculate things like length of stay or readmission rate. This is where you do your complex calculations on the underlying relational databases. It's also where you put your instructions on how the large language model should interpret the data in order to generate the best possible queries. Next up is orchestration. So you can create some value here with best practices and the tooling and how you set things up and making sure it's efficient. But I don't know if I'd necessarily call that IP most of the time. I still think at the semantic layer, that's where the agentic value gets created. The presentation layer is always important, but again, that's exposing the underlying value and making it accessible to whoever's consuming that value. Very rarely is the value actually created at the presentation layer. But this is where good storytelling becomes important, and the moral of the underlying story or the information within the underlying data needs to be exposed here in a way that the user can understand. It's not actually creating the story, it's telling the story. And then finally, you have outcomes, which is a summation of the entire process top to bottom. And again, step 3, the semantic layer, that's where an individual company can differentiate itself from its competitor. That's where a product can make itself more accurate or better than another product. So strictly from my perspective, if you own the semantic layer, you will own the value. Again, something I put together here with Microsoft 365 Copilot in order to illustrate why it's important to have good math with your data when you're building these agentic solutions. Right now in the tech world, all the big players are going around and saying, look, we can chat on your data. And most of the demos will sum up a column, show the result, everybody will clap. Wow, I can't believe that was possible. But the smart analyst or the business person who deals with data every day and is out in the real world, they will look at that solution and they'll say, how about inventory turns for the rolling fiscal year, excluding weekend days and defective products? And if you ask a question like that, that level of complexity will very often break the tool. And savvy business people know that the wrong number is worse than having no number, because making a decision with bad data is very often worse than making no decision at all. As I mentioned before, I work in the healthcare field, and I once heard a CMO, a chief medical officer, make a comment after viewing a demonstration about older AI tools before large language models and OpenAI and all that good stuff. Their comment was, all these tools are fantastic and we see the potential, but we think about something that tech people don't always think about. What we think about is if somebody uses one of these tools and they get an answer and it's the wrong answer and they make a decision based on that answer and somebody dies, who's responsible? And if you're out there building agentic solutions, that's the type of question you need to think about. It's not just all the wonderful things you can do with these tools, but it's also how do you use them responsibly and how do you prevent the flip side of those great use cases from happening? Because we all know that AI and large language models can present things that sound very accurate and present them with great confidence. And we need to make sure that what's being presented actually should have great confidence around it. So here's a very simple example to illustrate my case. If somebody goes to a chatbot and asks, what are the sales this year at Acme? The chatbot might respond with a number that reflects the current year from the data. But what if that company always talks in fiscal years? The chatbot won't know that unless you have some mechanism to instruct it what a fiscal year is. And what I mean by that is rather than filtering for 2025, a fiscal year would be anything that's greater than or equal to July 1st or whatever the start of your specific fiscal year might be. So when you ask a chatbot something about a year, it needs to know if you're talking about a calendar year, a fiscal year, a rolling year, year to date of the last day with data. The context matters. This slide is completely overbuilt and complex by design. I did it in order to prove a point. It's from a presentation I did about 2 years ago, which is also on my YouTube channel if you want to check it out, called The Evolutionary History of Microsoft Fabric. What is Fabric and where did it come from? And if you look all the way to the left on this slide, you'll see a little purple box called Panorama. Panorama was a company acquired by Microsoft over 25 years ago. And they built a product which eventually became OLAP cubes within SQL Server. And this was the first iteration of what eventually became a semantic model within the Microsoft world, which is now within Fabric. And the reason I added this slide here is because semantic models are effectively the perfect tool for talking to large language models and working within AI agents. The reason being is that they were designed to run really fast queries when you have extremely complex logic and to be designed in a way that a business person who's not technical can understand. And what we know about large language models is that you write good prompts by having good communication skills. Effectively, somebody who calls himself a prompt engineer is very usually somebody who has good social skills. And semantic models were fundamentally designed in order to serve that purpose with real people, but coincidentally, they also work very well with large language models and AI. If you go back several years, there were companies out there saying Microsoft has these semantic models, it's a waste of time, it's a wasted layer. But now all those same companies are saying, hey, we have a semantic model too, and ours is brand new, but you should use ours. If you go search for AI and semantic models out on the internet today, you'll see that everybody now is trying to build their own semantic model. Semantic models within Fabric are extremely mature. They've been around a long time, and they are a blazing fast query engine that can be understood easily by both people and large language models. I won't spend a lot of time on this slide, but with Fabric, semantic models, there's a few different ways to connect to data. There's the three modes which are shown here, which are direct query mode, where the Fabric semantic model will actually generate SQL queries or a relational query that goes back to a source database that actually processes the query and returns the results. The second is import mode, which has been around a long time, where the semantic model actually pulls data in, compresses it into a columnar database, and then the front-end users will generate queries from the reports or Excel or whatever tool they're using, which run directly against that columnar database. The benefit of import mode is that it works very well with complex multidimensional queries and high user concurrency. Thirdly, there's also direct lake mode, where you can think of it as effectively taking import mode and replacing the columnar database with the Delta Parquet files that are sitting in one lake or that are coming in from a shortcut. There's also ways to use semantic models with Fabric real-time intelligence. And there's another mode called a composite model where you can combine something like direct query with import in order to maximize performance at scale. So the reason I brought this into the presentation is that regardless of the type of structured data that you need to query in order to get good logic and good math, there's an architectural variation to meet that need. Again, I'm in healthcare, so I'm just going to try to explain to you how a simple question can actually be very complex when we're talking about trying to get good math from a question that you ask a data agent. So let's just say that somebody at a hospital asks, what is the average length of stay for Dr. Smith's MI patients? Sounds like a simple question, right? In order to make that happen from a relational database, these are the steps that usually need to be executed. First, you need to filter the data for the primary physician, Dr. Smith. You need to filter for inpatients. And MI stands for myocardial infarction, so that needs to be the filtered admitting ICD diagnosis. Next, you need to filter for the relevant time frame. When somebody asks a question like that, what do you respond with? For the year, for the month, for the week? Are we talking about yesterday, for their entire length of employment? What is the time frame? Next, you need to remove the exclusions. Maybe patients who died aren't included in those results, or if somebody gets discharged to another facility, maybe that doesn't count. Once you've done that, you need to sum up the total eligible days for all the patients in the cohort, and that'll be the numerator. Then you need to sum up the total number of visits that are qualified, and that's your denominator. Then you divide the two in order to get your result. It's probably a good idea to also add some qualifying information to the response, such as how many total patients did they have, because if the length of stay is 4 and they had 1 patient, the context is very different than if they had 100 patients. And how does that compare to their peers or their goals? And were there outliers where specific patients drove that number up or drove that number down, and maybe the mean is better than the average? Long story short, if there isn't some sort of contextual layer or semantic layer in order to instruct the data agent how to go get this number the right way, it's going to be very hard for a large language model to just guess. So again, moving to a Microsoft 365 Copilot slide that I built here, all-time historical understatements. With the invention of fire, the first people who came up with fire probably said, I do believe that this might be a little bit useful. And I don't think that Thomas Edison actually said this, but I do know that there were some articles written at the time that grossly underestimated the potential for the light bulb. Saying this is the light bulb with electricity. It has potential as a nighttime visualization tool in carnival sideshow tents. If we look at everywhere that electricity is used today, the people who invented it and when Thomas Edison came up with the light bulb probably had no idea of the scale of where it would be useful here in the 21st century. And then thirdly, this is one that you hear a lot, is that Power BI is just a data visualization tool. Well, semantic models are part of Power BI and now part of Fabric, and they are much more than just a data visualization tool. It is the logical layer that will become the value layer for AI agents that need to do math. So next, I'm going to walk through some best practices that you can implement in order to get good results from your semantic models. I'll also show some demos on how to actually do this in the real world. And again, all the demos that I'm showing can be reproduced from a free GitHub repo so you can deploy it to your own tenant and try everything that I'm showing out for yourself. The most important layer is that data model design. This layer has nothing to do with AI. However, it is now important to consider how you design it in the context of AI. Traditional data modeling best practices will improve your results for AI. So it'll do two things. It'll make the queries faster if you do the data model correctly, and it will also present the data or the metadata around the underlying data in a way that is easily understood by the large language model so that it can properly create the best queries. Next up, number 2 is traditional structured semantic model design. There are features in Fabric semantic models that have existed a long time, which can help optimize the results that you're going to get from AI when you're building agentic solutions that require math. And as I note on the right, these hard-coded design choices will add unbreakable logic to prevent hallucinations, improve the query results, and improve the query times. And I can't stress how important it is to have that unbreakable logic at the bottom layer. We want these AI agents to have as little room for error as possible, and this will minimize the odds of a bad query getting generated from a front-end tool. Number 3 is unstructured metadata design. There are now some tools in semantic models and in Fabric data agents that allow you to give instructions for that large language model to use the data appropriately. So it could be something as simple as when somebody asks about John Smith, rather than entering in John space Smith, enter in Smith, comma, space John, because the underlying data might always put people in the format of last name, first name. And then finally, there are things you can do at the edges and external tools, especially when you're using Fabric data agents to instruct how things get passed back to the Fabric data agent. I like to refer to this as design at the agentic edges. Now, when we talk about that first layer in data model design, I'm going to keep it simple with this slide. What type of data model should you use? And there isn't a perfect answer because every solution can be different. But in general, you don't want to use a denormalized database because that adds unnecessary complexity and query overhead. You don't want to use what I would call a supersized star schema, and I'll show you what that might look like in a little bit. There are circumstances where a flattened table of data makes sense. For example, if you're using Fabric real-time intelligence and you're looking to stream data, sometimes you don't want to break it into a multi-table design. But in most cases, a simple star schema will often produce the best possible results. And I'll explain that in a little bit as I get into the demo. So try to avoid denormalized and try to use simple star schemas with an understanding that sometimes a flattened design might make sense and get the job done. So when we talk about a supersized star schema, this would be a fictional representation of what that might look like. And I've seen these out in the real world where they work great and users get the results that they want. But each of those boxes is a separate table in the semantic model. And each of those arrows is a relationship that exists between those different tables. And you have to think in terms of what is the large language model doing when it gets a question and it's trying to generate a query. The large language model has to interpret the metadata for the entire semantic model. And if you're passing 60 tables worth of metadata with 120 different relationships between those tables, and the word date might exist 5 different times in the column names, it's going to be more likely to hallucinate because it has more opportunities to hallucinate. So keeping things simple, especially at this point in the maturity curve of where AI and large language models are today, is going to get you better results. So again, 5 years from now, maybe AI will get to the point that we've reached AGI and it can just look at this and understand it in a split second. But today, keep it simple. Now, I want to reiterate that everything that I'm going to show in the demo can be completely reproduced from our GitHub repo. I built this repo together with my counterpart, Inder Rana. We were on the same team for the last few years. And the entire demo can be deployed by downloading a single notebook, uploading it, and pushing the run button without having to know any code. Inder built out that automation process, and it's actually incredibly fantastic. So it'll be very easy for you to actually upload and use everything that we're showing you here in the video today. If I quickly move over to the GitHub repo and I go to the Analytics BI Direct Lake Star Schema module, this is where the instructions exist in order to do that quick install for everything that I'm going to show today. And I'll just quickly walk through what you get. when you deploy this. So a single notebook will reach out to CMS in order to get their Medicare Part D data set. So I think it's up to 275 million rows of data. It'll use a Spark notebook to pick that data up from the internet, drop it into Fabric OneLake. Then another Spark notebook will combine all of those years of data into a single table. And then another Spark notebook will be used to create a simple star schema with one fact table and 4 dimensions. And then it will also deploy a semantic model that's optimized for AI, along with the Power BI report and a Fabric data agent. So everything we're showing today will be up and running and ready to go in your environment in less than an hour. Now, here's what the semantic model from that GitHub module looks like. And you can see that there's a fact table for drug costs sitting in the middle, and then there's 4 dimensions that connect to it. And why does this model make sense for AI? So first of all, each table will group the columns in a meaningful way. So each row in the geography table represents a geographical location. In this case, it's a city. And when the AI reads that table metadata, it will know that in a geography table with a city, that if there's a column for state, that represents the state that the city is in. If there were also latitude and longitude numbers in this table, which there aren't, it would also know that the latitude and longitude correspond to the city, which is on that row. If you just had one big flat table of data and there was a column named state, the large language model isn't going to know, is that the state for a city? Is that the state where something was manufactured? Is that the state where something was purchased? Is that the state where something was transported? It won't know the context of why that column is there. Also, the relationships between tables are hard-coded into a semantic model. So it will know that when you're looking at a city, how do you filter the things on the fact table? So if you're looking at something like cost per day, it will know that that relationship needs to interact with that calculation in a specific way. And you don't have to build that into the prompts within the large that you're sending to the large language model. So you're able to reduce the amount of tokens that you're using in order to instruct the large language model how to generate a query. As I mentioned earlier, star schema designs generally, not always, but generally, will provide the most efficient queries. So when we're talking about queries where people select a bunch of filters and look for an answer, those types of queries are generally going to run the fastest when you're using a star schema. And there's a lot of technical reasons behind that. I won't dive into that today, but that's been, a known principle for a couple decades now. And as I mentioned, if you flatten out the table, you can confuse the relationship that the columns have to the underlying fact table and make it a little bit more difficult to consume. Again, if you have a simple flattened table of data, that's probably not going to be the case, especially as the large language models get better. But in general, today, you should see a little bit better hallucination rates by using a star schema versus a flattened table of data. And then finally, use business-friendly names. So you'll see that I named the tables things like drug, geography, provider, year, and you'll see the little eyeball with a slash through it for things that are hidden. For example, drug key, max year, min year on the drug table. And the things that are exposed have good natural language names like brand name and generic name. Now, I'll quickly show an example of how to actually configure these things, but a few general best practices. I think the documentation for these types of things is getting updated soon, so there'll probably be a better list than what I have here at some point very shortly. Hide all the key values. The large language model doesn't need to read the key values, especially if you have the relationships baked into the semantic layer. Hide the implicit measures. Those are columns that are summed up, averaged, max, min, and then build explicit measures where you're actually hard coding in how do you do average revenue? How do you do total revenue? How do you do median revenue? How do you do year-to-date revenue? Explicitly build each of those into the semantic model so that every time somebody asks for that type of calculation, it's going to get the math 100% correct. When we talk about semantic models, we talk about DAX codes. Keep it simple. It's now a best practice to add your synonyms to the AI instructions, which is the unstructured layer, and make sure you add those for your explicit measures. Get the formatting right. So for every single column, think through, do you want 2 decimal places? Do you want 1 decimal place? Do you want commas? Do you want a dollar sign? And if possible, I always say to try to hide all the columns on the fact table except, worst case scenario, degenerate dimension. Then with your dimension tables, again, hide the key values, only add measures to dimensions if you need to. Anything that's numeric, such as year, set it to do not summarize. Hide anything you don't need. Add your synonyms for both the table name and the column names to the AI instructions. And again, use business-friendly names. Okay, so for an example, I'm here in Power BI Desktop. If I go to the model view for my data model, you'll see it's a version of what I just showed you in PowerPoint. If I were to click on a table, you'll see that we get the information over here on the right as far as what is the name of the table. What are the settings as far as the storage mode? Per my slide earlier, is it import? Is it direct query? Is it direct lake? If we're looking at an individual column, you can see, what is the data type? What is the format? If I were to look at something like prescriber state, that's where I could scroll down here and set it the data category to, let's say, state or province. And that's going to instruct the large language model that this is a geographical location that it can put on a map. So you want to do all these types of optimizations here in the data model design. And when I'm talking about the DAX expressions, you'll see here, cost per claim, you divide the total drug cost by the total claims. So whenever somebody asks about cost per claim, it's going to make sure that it's dividing the correct numerator with the correct denominator. And that if somebody has asked for a specific drug or a specific year or a specific provider, that all of those filter contexts will be passed to that equation to make sure that you get the results which are accurate. You'll also see that a lot of stuff is hidden here, because if you don't need to pass these columns to the large language model in order to figure out how to write a query, don't do it. Just send it what it needs. If I go back to the designer page here in Power BI Desktop, you'll see up on the ribbon, I have prep data for AI. There's an option here after you get started to simplify the data scheme. And by hiding columns, it will automatically remove them from what the AI is able to view. But you'll see here that for the fact table, I am just exposing total claims, total day supply, and total drug cost, along with cost per claim and cost per day. So those are the only things it's going to see from that entire table, because those are the only things it needs to see. So very carefully think out what needs to be exposed for each of the different tables within that model. There's a capability called verified answers. You can go search for it on the internet. It's very simple. When you're looking at a report inside of Power BI and you're in edit mode, you can select a visual and contextually decide how it should be used for specific types of questions. So this example is where somebody might ask a question similar to show cost per day of medications. I'm instructing it to provide results that look somewhat like this. So it will default to this type of visual and this type of format when somebody asks a question of that nature. Next, there's the option to add AI instructions. And this is where you need to put a lot of careful thought and consideration. The context of how questions get interpreted by the large language model, a lot of it is driven from this layer. So here you'll see, for example, that I'm listing out each individual table and each individual column within that table, and noting, for example, that the table provider is a dimension table with a list of providers, doctors, and prescribers. The format is always last name, comma, first name. The column prescriber full name is their full first and last name of providers, doctors, and describers, and always use this column for providers or doctor names. Moving down to some additional information that does not exist in the database. For example, I note that all ACE inhibitor drugs contain pril within the generic name of the table drug. So the word ACE inhibitor does not exist anywhere in the underlying database at all. But if somebody says, show me the total cost for ACE inhibitors, it will now know that if you look for generic names that contain pril, you can filter the data accurately. Now, best case scenario, you actually add a column to the drug table that flags the ACE inhibitor drugs so that you make sure you get it right every time. But this is just an example of how you can use unstructured instructions, or what I like to call unstructured metadata, in order to generate accurate queries. And then down at the bottom, I'm also providing an example of how you can instruct the large language model that you use the word internal medicine in the filter whenever somebody asks about internists or anything related to internal medicine. Now, there's a lot of ways that those AI instructions can go wrong, and there's probably going to be a lot of opportunities to improve on your first cut at those instructions. And that's where a rapid prototyping, iterative process needs to be in place in order to optimize those AI instructions. So every time you make a change, go test it. When you deploy it to the users, let them know that this is the beta testing version and we need your feedback about what works and what doesn't. And then go back, change those instructions, retest, and it literally takes less than a minute to paste in new instructions and then rerun the queries and see if you get better results. So you can rapidly iterate through these cycles in order to get the best possible results based on your own unit testing and also the feedback that you're getting from users. This demo was recorded in early November of 2025. It's based off of a presentation I did at SQL Saturday, Minnesota in September. And I fully anticipate that within a month or two, a lot of these concepts will be even further along from a roadmap and development perspective. And there may even be new capabilities that have been added. This is a rapidly evolving area. But let's go ahead and walk through what that actually looks like in the real world. So here in my Fabric workspace, if I click on the semantic model, you'll see in the upper right, prep data for AI. There's some different steps you can do to optimize your semantic model for AI. And one of those is also adding the AI instructions. These AI instructions will allow you to interpret context correctly so that it gets translated into an accurate query. Here in the Fabric portal, you'll see there's an option for the Enterprise Copilot. If I open that up, I can start asking questions about my data. So let's use that semantic model and let's say how many rows are in this solution. In this version of my demo, I have about 250 million rows. We have a repo where you can deploy this entire solution end to end in less than an hour by clicking a single button. The only cost would be the compute that you use within your Fabric environment. Let's go ahead and ask it another question. And let's say show cost per day and cost per claim by provider type on a scatter chart. The bubble size should represent total cost. So a large language model will take that text and it will translate it into a query which can be run against your semantic model. And because we hard-coded all of the information about relationships and equations and things like that into the semantic model, it'll give you accurate mathematical responses. You can see it's responded with a scatter chart. And if I were to hover over one of the bubbles, it's telling me the prescriber type, the cost per day, the cost per claim, the total drug cost. You'll see we have an outlier here for medical genetics and genomics, where there's a very high cost per day because they're dealing with such a specialized area. That's the most likely cause. I don't actually know that. Let's ask another question in order to get the scatter chart to be a little bit more readable. So let's say try again, but filter out provider types with a cost per day above $50. Now you can see we have the same data as the first scatter chart, but we've eliminated that outlier so that we get a little bit better view of the data in order to try to understand what's going on in our system. Now let's make that a matrix. And this will just give us the actual data rather than a visual so that we can look at those numbers in a little bit more detail. Here we now have the prescriber type with the cost per day and the cost per claim. If I were to click on cost per claim, you'll see that it resorts the list based on those results. Let's ask another question. And let's say, using the above results, can you figure out which drugs are causing the greatest impact, both from a total cost and cost per day perspective? Hit go. And again, as I mentioned before in the first query, this is working on 250 million rows of data. So this is not a small optimized set of data, which is intended to make the tool look better than it really is. Here we now see a list of which specific drugs have the highest cost and the highest cost per day. Now let's ask another question. As you remember, the outlier in that first graph was hematology-oncology. So let's repeat the above report, but only for hematology and oncology. Okay, now you can see it even gave us a small summary. Based on the available data, certain drugs have the highest total costs, while others stand out for their exceptionally high cost per day, indicating significant financial impact from both volume and price extremes. But what if you want to be able to chat on that data from outside of Power BI or outside of Fabric? If I move back to my workspace, that's where the Fabric data agent becomes relevant. If I go ahead and click on my data agent, you'll see that we're connecting to that same semantic model from the data agent. It'll use the instructions that I've added to the AI instructions and the prep for AI portion of that semantic model. And then once I publish this data agent, and you'll see under publishing, there's now a API endpoint that's available. You can call this endpoint from tools outside of Fabric and Power BI. So for example, if I am in AI Foundry, as I am here, you'll see that I've added that endpoint, that Fabric data agent, to this custom design within my agent. I could now couple this API endpoint, which gives me good mathematical results on 275 million rows of data, with other types of content such as embedded PDF documents or specialized prompting instructions in order to have a more robust and capable agent outside of Fabric and Power BI. The end users won't even know this is coming from Fabric. Additionally, if you're using Copilot Studio, you can do the same thing. You can add that Fabric data agent as an API endpoint simply by clicking a few buttons, and then you can do whatever else you need to do to have agents within teams that are easy to build and that can access data from many different places. So in conclusion, by having this robust and carefully thought out context and configuration layer within your stack, whether it's for use with Power BI Copilot or if you're using the data agent for external tools, you are able to provide good mathematical query results on top of your data that will be scalable and provide a great foundation for AI in the future. So in conclusion, I'm assuming most of the people watching this video work in the data world, and you will not be replaced anytime soon, especially if you become skilled in helping to prep and architect data for AI. And going back to the earlier use case of the satellite crashing into Mars because one team used pounds per second instead of newtons per second, the industry is going to need people like you in order to build good, solid data foundations for AI so that agentic solutions and chat on your data can get good mathematical results from the underlying data at scale. And again, here generated by M365 Copilot, I don't think that you will be replaced anytime soon by an AI agent named Fabulous Rick, who goes by Fabric. There is still a career path for you in this new era of AI. Thank you for sticking through this presentation. If you could like the video and follow the channel, that would be great. And as mentioned earlier, all the demos that I showed today can be deployed in less than an hour from a free GitHub repo that is linked in the description below.